I'm ready for an extra adventure here, the one sample t-test. I'm here with my son Tyler. Tyler, can you say hello?
Hello.
And Tyler, is 5 years old enough to be able to teach statistics?
No.
Okay, maybe not quite old enough. Tyler, what's going to happen here with this boulder coming down, do you think? Can you say?
It's going to knock off the van.
Well, maybe. He's got a pretty good grip there. He might be able to make it. All right, a quick overview. There are two main changes from the z-test. First off, we're going to have a new formula. So that's our old formula, z formula. Now we're going to have the t is equal to the sample mean minus mu divided by standard error as a population estimate. So you'll notice this thing on the bottom changes. And that will mean we're dealing with a different distribution. So whereas before we were dealing with the z distribution, the standard normal curve, which never changed, and we always had the same z critical values, that 1.96, we're now going to have a distribution that changes based on how many people we have. The more people, the more accurate we get. And we'll see that we have a different cutoff value, a different t critical for depending on how many people we have, how many degrees of freedom. All right, we're going to do a little more in detailed comparison here between z-test and t-test. This is still just an introduction, so don't panic. All right, for the z, we would have a question like, is the debate team dumber/smarter than normal? With 9 students who have a mean of 125, standard deviation of 15, and a mu of 100. Well, we could quickly figure out the standard error is equal to 5. That's the variability we'd expect just by chance. And then we can plug that into the z obtained formula for a sampling distribution, and we get a z obtained of 2. Well, is that extreme? Does that say the debate team is smarter than normal? We would plot that in our z distribution, where we always have the z critical cutoffs of 1.96 and negative 1.96 if we're working on our 5% rule. The z obtained would fall past that. It would fall in the end zone, this region of rejection, and we would say that, yeah, the z obtained is greater than z critical, so we can reject the null and say that the debate team is smarter. A t-test example, you'll notice we don't have standard deviation in the population. All we have are some x's. So is the average tip smaller or bigger than normal? So some waitress or waiter gets these tips on average in the whole population. They're supposed to get an average of 5. Well, there's a standard deviation of 1.63. Let's assume you just calculated that by hand. That's an estimate based on these numbers. And so then we get standard error is equal to 0.82. That's the difference that we'd expect just by chance. And then we do the calculation on top to get the difference that we observed. And that works out to a negative 2 point something t obtained. So if we assume that we're working with the 5% rule, which we're going to call alpha, is equal to 0.05, we work out our degrees of freedom, which is a way of taking into account how many observations we're dealing with. We would go to the table in the back of the book, and we would see with 3 degrees of freedom, we have a t-critical value of 3.1824. So, whereas over here with the z, a 2 was good enough to reject, over here, since we have so few subjects, our t obtained does not exceed our t critical. It doesn't get back past that 3.1 on the negative side, so we have to retain the null and say that these tips are the same, or it's conceivable that those tips come from a population where mu is 5. Okay, so that's just a quick overview. We'll go in more detail here as we go. Okay, so the z-scores and t-scores are very similar. They're both providing a way of judging how extreme a sample mean is, and a bunch of t-scores form a t-distribution, just like a bunch of z-scores formed a z-distribution. We do it when the standard deviation is unknown. So a classic case, which we'll do in class, is let's say you wonder if college students really get 8 hours of sleep. Well, you have a mu there on which you can form your null and alternative hypotheses, but we don't have standard deviation in the population. So we would do a t-test, and it's the t-distribution that provides the foundation for a t-test. And the t-distribution, it's a modified standard normal curve. So it's still the bell-shaped thing, but the bell shape is a little different depending on how many observations you have. So the key difference from the z-test, it's done when the standard deviation is unknown, and you have to estimate standard deviation using the formula for S. Okay, so reviewing here, we got to go back and remember that there's two ways to calculate standard deviation. If we have all the scores in a population, for example, like the SAT, where you have every single score, you're going to be able to calculate standard deviation using the population parameter formula, where we don't have to adjust for n-1. However, many times in research, we have scores from a sample, and we're trying to estimate the variability in a population. So, for example, like I was talking about the college students and how much they sleep. If we just take a sample, say, of 12 students and ask them how many hours they sleep, that's not going to give us a standard deviation of the population. We'd have to calculate it based on those values that we have in the sample. And again, you'll notice the main difference here, if it's an estimate, we're using the S formula and it has the n-1. So this is the land of z-tests, this is the land of t-tests. All right, so we have to have a different measure of standard error. If standard deviation is known, you can do a z-test because you can calculate standard error as a population parameter. Shazam, you get z with that measure of standard error down here. But if you don't have standard deviation, you have to do a t-test. In other words, you have to get standard error based on this thing, which is an estimate. And since it's an estimate, that's going to change the t calculation because this on the bottom is going to be different. Okay, you'll notice that here, if I have the sigma, it ends up with something with the sigma, and over here, if I have the s, it ends up with something with the s. So once we start estimating, we're in this world of the t-test. Okay, so the shape of the t-test is going to be different based on how many people you have. So this is the normal distribution, right? The one we've become accustomed to. The t-distribution is going to be shaped slightly differently because it has more variability. It's more spread out on this line. So it's going to be shorter here in the middle. There's going to be less common scores, and there's going to be more extreme scores. So you see this shaded area here? That's the difference. That's where you're going to have more extreme scores. So it's shorter, and the tails are fatter, representing more variability. So the key thing, estimating that standard error down there gives us more variability. It changes the shape of the distribution. All right, so the rule is, as n increases, the t-critical is going to decrease. So let's work this out in a little more detail. So as n increases, the degrees of freedom increase. So in other words, getting more people is a good thing. It gives us more degrees of freedom, which we like. And the t-critical will shrink as your degrees of freedom increase. In other words, it gets easier to reject the null. So more people are good. Makes it easier. And with the more people you get, the more the t approaches a z distribution. So if we look at this graphically, if you look here at the red line where I just have a paltry 3 degrees of freedom, that's pathetic, right? That's embarrassing if you had 3 degrees of freedom. That's only 4 people. The red line, in order to reject something, I got to get clear out to 3.18. I have to go a long ways from the middle to be able to reject something if I just have the degrees of freedom equal to 3. You'll notice when I go up to 6 degrees of freedom, things get better. Now I can start rejecting at 2.45. In other words, I don't have to get the sample mean out as far before I can say there's a significant difference. Same thing over here on the negative side. And then as you go from blue to an infinitely large sample, you actually make the t-test into a z-test because an infinitely large sample is the same as having the population, and so we'll see we have the z-score critical values of negative 1.96 and 1.96. So again, notice how this error gets smaller. We move from the red line to the blue line to the black line when our degrees of freedom increases. In other words, when we have more people in our sample, we get more accurate, and the estimation causes us less problems, and we get closer and closer to that negative 1.96 that we'd see with the z-test. Okay, let's work through a simple example here. Let's say there's some cars that are going by your house averaging significantly, you're curious if they're going significantly slower or faster than 55 miles an hour. And here are the values that you get. So 45, 60, 65, 55, etc. Let's assume that you went and stole a police radar gun and were sitting on your porch as these cars went by, and so that these are accurate measurements. So in the steps of hypothesis testing, of which there's 5, the first thing you do is just simply say what you're comparing. In this case, this will change later, but for right now, it's always X bar compared to mu. In other words, the sample mean compared to the population mean. So in this case, what I'm interested in, I'm testing this value of 55. My null is that mu is equal to 55, and my alternative is that mu is not equal to 55. I would do a two-tailed test, which is what I always do, and the alpha is equal to 0.05, which is typically where I always set it, and degrees of freedom is always equal to n minus 1 with the one-sample t-test. So how many participants do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 8 degrees of freedom. If I look at the table in the back of the book, with 8 degrees of freedom, I get a t-critical value of 2.3 something. Okay, then, if that's the number to beat, I got to see if I can beat it with these scores. So I'm going to calculate t obtained. How does that work? Well, the first thing you have to do is calculate standard deviation based on all these raw scores. So this is the old school. Remember, you line up the x's, the x squareds, you calculate the sum of x quantity squared, the sum of x squared, and you plug in to your standard deviation formula, and you'd figure out standard deviation. So the standard deviation among these scores is 7.8174. So we figure out standard error, again as an estimate, sticking with the S, and our standard error comes out to 2.606. And remember, what that says is that's the variability we'd expect between a sample mean and mu based just on sampling error. So if it's a little different than 55, we're not going to be wildly surprised. The third step, there's always 3 here, is we actually calculate t obtained. So on the top, we have the difference we observed. So I figured out, based on these scores, if I added them up and divide by 9, I'd get a sample mean of this. That minus the population mu is the difference that I observed. The difference that I'd expect just based on sampling error is that 2.606, and that gives me a t obtained of 1.492. Now, ask yourself, does that t obtained fall into the region of rejection? Does it surpass that critical value? And you would say, no, it does not. So why? Let's look at that more carefully. So here's my null distribution, where mu is equal to 55. I'm going to slap down my t-criticals at negative 2 point something and positive 2 point something. That defines my region of rejection, what we'll later call the alpha area. That's equal to 5% of this entire distribution. Well, then I locate my t obtained, and it falls short of the promised land. It is not in the region of rejection. So my conclusion is I retain the null, and then later you're going to learn, I shouldn't say later, soon we're going to start writing it up like this. The kind of explanation you would give is the hypothesis was not supported. Average car speed, blah, does not differ significantly from 55 miles per hour. And then t with 8 degrees of freedom is equal to whatever t obtained was. And then this last part tells me if it was significant. Here it's not, so it's N period, S period for not significant. But 2 parts. The first part, you're just stating the hypothesis, whether or not it was supported. And then the second sentence is comparing the 2 means, the 58.89, the sample mean, and the 55, the population mean, and then telling if that statistic was significant. So that's it. Okay, in class we'll do the example here with 8 hours of sleep for college students, and you'll work that out. Let's work on another problem while we're just on the video here. So example number 3, the critical thinking test. Let's assume that we had 45 people take the, can you pronounce this? It's the smarter than you, get it? Smarter than you critical thinking test. College graduates score 35, 45, Are college students worse or better at critical thinking? So do these scores from people that have taken the critical, that have gone through college, do they do better on this critical thinking test than the average score of 45? See if you can fill in the 1, 2, and 3 here before we move on in terms of the first 3 steps of hypothesis testing. Why don't you hit pause and then hit play when you're ready? Okay, so you should have gotten the following. You're comparing the sample mean and mu, which is what we're going to be doing for a while here. Second step, you state what the null and the alternative hypotheses are. So mu is equal to 45, or mu is not equal to 45. And then you set up the details of your test. Well, we're always going to do that two-tailed test. We're almost always going to say alpha is equal to 0.05. Degrees of freedom is just n minus 1. We got 9 participants, so 9 minus 1 is 8. And then we got to look up that t-critical value in the back. So this is the one we had before, right? Because, again, we have 8 degrees of freedom. So we'd get the same t-critical value. Now, excuse me, I'm giving you a hint here just to get you started on what the standard deviation is. But to get that, you would have to do by hand all the math to get standard deviation. So at this point, if I give you this, see if you can figure out exactly what t would be equal to. Go ahead and hit pause and hit play when you're ready. All right, if we are given the S value of 10.6066, the standard deviation, we'd have to get standard error, first of all, and that would work out to 3.5 something. And then we could plug that into our t formula, and we'd have to figure out the sample mean as well. Just take all the scores and divide by 9. And we get a t value of 0.4714. Is that enough that we can reject? No, this is pathetic, right? A t value even less than 1 is never going to be significant. Your mother even would laugh at you for getting this. So, how would we write this up? We're comparing the x bar and mu. Our null is that mu is equal to 45. The alternative is that mu is not equal to 45. We set up our values here to get that critical test value, and we got a t obtained of 0.4714. So, see if you can fill in the correct bits and pieces here on your own, and hit pause and hit play again when you're ready. Okay, so you should have gotten the following. The hypothesis was not supported. College graduates did not score significantly better on critical thinking. So that sample mean of 46.67, even though it's bigger than 45, it's not big enough that we trust that difference and we can call it significant. We're forced to retain the null hypothesis. We would summarize the statistic as follows. T with 8 degrees of freedom is equal to 0.4714, comma, and it's not significant in period S period. Here I'll give you a summary table of some of the different statistics we've calculated so far. If you have a frequency distribution and you have a single score, you calculate a z-score for a score. If you have a sampling distribution, and you know all the scores in that distribution such that you can calculate the standard deviation and the standard error, then you would do a z-test for a sampling distribution. And then our new test here, where again we're dealing with the sample mean, x bar, and in this situation we're going to have to estimate standard deviation. It's when we are not given the standard deviation of the population, and so that's when our t formula is a little different. But you'll notice all these formulas are very similar, and you should be able to compare and contrast and see why they change slightly. Okay, and then let's work through an example of how it would work on SPSS. Again, let's go back to the cars example. So the government claims that the cars traveling in front of your house are averaging 55 miles an hour. You think this is a load of donkey stuff. And so you steal that police radar gun, which you'll give back in due course, along with a thank you note. And you collect the speeds here, 45, 60, 65, da-da-da-da-da. So just eyeball those. Does it look like those are significantly larger than 55? Well, yeah, but there's that 50 and that 45, so it might be close. First off, what's mu? Mu is the number you're testing against, which in this case is that 55. It's typically a number that's just hanging out by its own, not associated with the specific group. So, in SPSS, we would first type in the numbers, and then we would come over here and go to Analyze, and go to Compare Means, and go to One Sample T-Test. And then that'll cause this screen to pop up, and we'd move over the variable we want to test, in this case speed. And here's the critical thing: don't forget to put what you're testing against, because otherwise it'll be set to 0. You want to test to 55 miles an hour. Then you hit OK, and you will get output. 2 tables. First one, descriptive statistics. It'll tell you the number of cars that you measured, the sample size. It'll next tell you the average speed of these cars, the sample mean. Then it'll tell you the standard deviation of those speeds. And then it'll tell you the standard error of the mean. So that's the typical difference you'd expect between this and the 55 miles an hour based just on sampling error. Then you actually get the test, the one sample t-test. This is the formula by hand, and you should be able to relate that to the information here. So that's your t obtained value, that's your final t value, and you're testing relative to 55, that's the mu. And then if you combine those two, the sample mean and mu, there's a difference on top of 3.89, and then we would divide that by the sampling error that you saw on the previous screen, the standard error, and you would get a certain t-value. Now on the printout, you also get this significance value, or this p-value, this p-obtained value. And just like with correlation, that's the percent of time you're going to see something as a false alarm. So it's a proportion of time you'd see a difference of this size simply because of sampling error. So in other words, about 17% of the time, we'd see a difference between the 55 and the sample mean. This difference here, that 3.89, we'd see a difference that big about 17.4% of the time. So that's a little too risky. It must be below 0.05 to say you have a significant difference. It's not close. So guess what? We are going to be retaining, excuse me, a null hypothesis. This 95% confidence interval, you can always ignore that. We're not going to mess with that. So you'll note that there's no t-critical when you've done the test in SPSS. You can be even more specific because you have this p-obtained value that you can use. You don't have to just compare it to that static t-critical value. Okay, let's go through and see if you have the same test, but with slightly different scores, how you'll get a slightly different outcome. Okay, so what happens if you compare the mu and the x bar? Well, you should see that the sample mean now, if you compare back, it's what? It's a little larger. The cars are going a little faster. What did I do? I went back and I killed that 45 and I increased the numbers of these, the size of these other scores a bit. So, but standard error is roughly the same, but the fact that we have a bigger difference here between the mean and that 55 miles an hour, reflected here in the mean difference, that now compared to the standard error, in other words, taking this 6.11 divided by 2.469, that gives us our t-value, right, over here. Is that t statistically significant? Shazam! It is. The p-value here is telling us only 3.8% of the time would we see a difference this large, that 6.11, just by chance. So that's below the 0.05 level. So we can reject the null hypothesis. And just quickly summarizing that, we'd say like speeds appear to exceed 55 miles per hour, and then we'd summarize the t here. That's not the full write-up, but just that's exactly how the summary would look. It'd be having at the end there indicating a significant difference. Okay, let's do just time out just for a second while we work through this treatment effect versus sampling error. Anytime you're trying to find a significant difference, you're looking for what we call the treatment effect. And there's one of two ways. There's two ways to make it more likely that you could find a significant treatment effect. One is to cut down on this random error. So, in other words, in the cars example, to figure the things that are causing the variability in the car speeds, maybe the types of drivers or other things, the more you standardize that, the more any difference due to the treatment effect will stand out. Over here, the other thing you can do is make the treatment effect bigger. So this kind of logic makes more sense maybe when you think about like a drug study. Say you have some drug that's supposed to decrease anxiety. First step you'd want to do is eliminate all those other factors that might be influencing anxiety. And the second thing you'd want to do is make that drug have as big an impact as it possibly can. If you do both of these things, the T value will get larger. And as we go through the course, we'll relate the concepts of treatment effect and sampling error to the way the formulas work. Okay, so we have time now just for a quick learning check. Let's run through these, and I have the formulas printed here to help us think through things. As T obtained increases, we become more likely to do what to the null hypothesis? Well, as T obtained gets bigger, that means the difference observed is getting bigger relative to the difference expected. And as a rule, once you get started getting past 2 or 3, it becomes really likely you can reject the null hypothesis. So the short answer, as T obtained increases, we become more likely to reject the null hypothesis. If sample size increases, T obtained will do what, and T critical will do what? Well, other things being equal, if sample size increases, what happens? If sample size increases, that makes our estimate of sampling error more reliable, right? If N here goes up, standard error is going to go down. And if standard error goes down, that'll make T get bigger. So as sample size increases, T obtained will get bigger, and T critical will what? Well, remember, what determines T critical? It's the number of participants, so in other words, degrees of freedom, and then what alpha level you're using. And we're almost always going to use alpha of 0.05. So as N goes up, degrees of freedom will go up. We become more confident, and that makes we have less error, so T critical goes down. Okay, what happens if the difference between X bar and mu increases? So in general, is that a good thing or a bad thing? That's a good thing. If the cars going by your house are only going 57 miles an hour compared to the expected 55, that's not so great because that's a small difference. But if they're going 107 miles an hour versus 55, you're like, whoo-hoo, I can call that a significant difference. So let's work through this logic. If I change the top part here, does that do anything to sampling error in the bottom? No. So sampling error will be unaffected. Remember, sampling error is only affected by changes in standard deviation and the number of participants. What will happen to T critical if this top thing changes? Nothing, because T critical is determined just by degrees of freedom, the number of participants, and whatever you set your alpha level at. What will happen to T obtained? T obtained will increase, because as this difference gets bigger, T will get bigger. What will happen to SX bar? In other words, the standard error as an estimate, that, again, will not change because that's only influenced by these two things. Okay, and if this difference on tops gets bigger, I'm going to become more likely to reject the null. Okay, one more learning check. A researcher compares the number of workdays missed for employees who are depressed versus the company-wide average of 6 days per year. So in this case, the null is going to be what? The null is going to be that mu is equal to 6. And rejecting the null would say that depressed employees are missing more or fewer days. B, would you become more or less likely to reject the null with a sample mean of 8 versus 10? Well, a sample mean of 8 would only differ by 2, whereas a sample mean of 10 would differ by 4. And that would make the top of the T formula bigger, and it would become more likely to reject with a sample mean of 10. Okay, then last question here. Would you become more likely to reject with a sample mean, would you become more likely to reject the null with the standard deviation of 1.5 or 3? So first ask yourself, do we like variability? No, we hate variability. So we'd rather have less variability because that makes the standard error smaller, and that means we're dividing by a smaller number on the bottom. If you look at the formula, that should make sense. So we'd be more likely to reject with a large sample mean and with a small standard deviation. Okay, so that's it for this part of the lecture, and we'll pick up with the next section in the next video. Thanks.